problems that we didn't get to in class today. So I'm going to start with number 11 here. And so in this one, so we have a volume. So it says the volume is measured at a certain temperature, and it's this volume. So that's our volume. And this other number, the 27, that's a temperature. And then it says, what is the temperature? So we're solving for the second temperature, or the new temperature, when the volume is reduced to 9 cubic decimeters at the same pressure. Okay, so pressure is staying the same. So that means that pressure is constant. So that means this problem only deals with volume and temperature. And so volume and temperature, so I have, like, this is V1. This is going to be V2, because it's the volume after the change happens. This one will be my T1, and then my T2 is what I'm solving for. And so if I read through that question, I should be able to identify all of those things. And then knowing that I have only volumes and temperatures, that means that this is going to be a Charles law question. And so that equation, if you look up in your notes, it is V1 over T1 equals V2 over T2. And we're solving for T2. So in order to kind of rearrange this equation, the first thing that I'm going to do, I'm going to cross multiply so that I can get rid of this division. So I'm going to rewrite it. So I have V1 times T2 equals V2 times T1. And then to solve for T2, I would divide both sides by V1, and that is going to give me just T2 on this one side. So now I know that's how my equation should be set up, and so now I can plug numbers in. So I'm going to clear off some space over here. So now if I come back here and if I plug my numbers in, V2 is 9. And then T1, here's the catch. T1 is 27 degrees Celsius. But if you remember up in your notes, anytime we do calculations with gases, we always need to change temperatures to Kelvin. Don't forget that. So I need to add 273 to that 27. And so it's actually going to be 300 Kelvin. So I have 9 times 300, and then the V1 on the bottom, that's this 10 from right here. And so you don't have a calculator, so you have to kind of remember that. But these are not necessarily hard numbers to deal with, okay? What you want to do is make it a little easier on yourself. So in my head, I'm just going to do 9 times 3. And so 9 times 3 is 27, and then I can just carry over my 100. So 2700 divided by 10, and anytime I divide something by 10, that's just going to move the decimal place back 1. And so 2700 divided by 10, that's 270. But remember, that's Kelvin. And if you look at your answer choices, they're all degrees Celsius. So I need to subtract 273 to get to my final answer. And so it's -3. And that would mean that it would be letter A. Okay. All right, so this next one down here, let me read this one. Okay, so this one says, at which temperature, so we're solving for a temperature in Kelvin. Notice that it does say we're assuming constant pressure, so that means that pressure is not going to be in our problem, okay? So at which temperature in Kelvin, assuming constant pressure, is the volume of a fixed mass of gas at 127 degrees Celsius doubled, okay? So they've given us a temperature here. So I'm going to go ahead and label that this is going to be T1, because that's originally the temperature. I'm solving for T2, because it says which temperature in Kelvin. Pressure's constant, so that means that the other thing I have is volume. And notice that it says the volume the volume is doubled. So this is one of those problems like we looked at in the notes where they don't actually give us numbers for one of the properties, but that's okay because that actually makes it easier on us because that means we get to pick the numbers. So if the volume's doubling, I'm going to pick V1. I'm going to make it 1 cubic decimeter, 1 cubic centimeter, it doesn't matter. And then if it's doubling, I'm going to make V2 2. Okay, so pick easy whole numbers on things like this where they let you pick the numbers. Okay, and then the only other thing I have to remember before I kind of start looking and plugging stuff into my equation is if I come back over here to this volume right here, this 127 degrees Celsius, remember I do need to change that to Kelvin. So I'm going to do 127 plus 273, and let's see, that's 10, it's 910, carry the 1, so 400 Kelvin is our temperature, okay? So here's where you can kind of go one of two ways. You can go the math route, and you can use your correct gas law equation, and since this one has volume and temperature, this is another, this is also going to be Charles' law, just like the number 11. And so since I'm solving for T2 again, it's going to be set up pretty much like this last one we did. And so I know that T2 is going to be V2 times T1 divided by V1, and then I can plug in my values. So I have 2 times 400 divided by 1. Okay, and then 400 times 2, that would be 800 Kelvin, so your answer should be D. But again, you don't have to go through all of this math if you just convert the temperature to Kelvin, and then if you look at the fact that it tells us the volume is doubling, if I know that volume and temperature have a direct relationship, so if the volume doubles, if the volume goes up, the temperature is going to go up by the same factor. So since they have a direct relationship, if the volume doubles, the temperature will also double. So I just need to convert the temperature to Kelvin, and then I can double it, and that's my answer right there. All right, so let's see, number 13. What is the pressure, okay, the pressure in pascals if 3 moles of gas, let me switch colors here. So 3 moles of gas occupies 500 cubic centimeters at 25 degrees Celsius, okay? So this is going to be an ideal gas equation because I have a pressure. I have a pressure, and that's actually what I'm solving for, okay? But the pressure is mentioned. I have a number of moles. That's my amount of my gas. I have a volume. Well, I will say the volume is cubic centimeters, and for ideal gas law, it does need to be, remember, it needs to be converted to meters cubed, so that's going to affect your answer. And notice they gave you the conversion right here, okay? So 1 times 10 to the negative 3 meters cubed equals 1 times 10 to the positive 3 centimeters cubed, okay? So keep that in mind that they'll give you information like that that you might need to use. And then, our temperature is here. So they give us PV, or N, V, and T. We're solving for P. And then I kind of accidentally wrote over it, but here is R. They give us the R value here. So we just need to make sure that we're plugging these in the equation right. The only thing is we need to make sure we convert some of them first. Specifically, we're going to need to convert the volume to meters cubed, and we're also going to need to convert the temperature to Kelvin. After that, it's really easy. It's just plugging it into the ideal gas equation, which from your notes, that's the one where it's PV equals nRT. And since we're solving for pressure, we would rearrange it to say P equals nRT over V. And so we're looking for the one that's going to have moles, N on top, R on top, the temperature on top, and the value for the volume on the bottom. What's going to trip some people up is they're going to forget to convert this volume. Because I can tell you right now that some of you guys are probably already thinking that it's one of these two because, oh, they have the 500 on the bottom. A lot of you guys would probably pick A. because that has the 3 for the number of moles, it has the 8.31 for the R, and it has the correct temperature because it has the temperature converted to Kelvin. So 25 plus 273, that's 298. What you guys are going to forget, you're going to forget that the volume for this equation has to be cubic meters. And so A cannot be correct because that volume has not been converted. So even if you don't remember how to convert the volume, so let's say that you don't remember how exactly to use this conversion, so you don't remember what the actual volume is going to come out to be, you know it's not going to be 500 because it's going to be much smaller because meters are a lot bigger than centimeters. So based on that, you should be able to eliminate A and C right off the bat because they don't have the volume converted from centimeters cubed. Okay, you will not just plug the 500 in. Okay, you have to convert it to the cubic meters. So then that leaves us B and D, and they both have the same number in the volume. That's been converted to cubic meters. The difference between them is B did not convert the temperature, D did. So again, you're not having to do all the math. It's really kind of like looking at your information and using it wisely to eliminate your answer choices, okay? If you know that temperature has to be Kelvin and that volume has to be cubic meters, then you should know 525 should not appear in your answers. And so the only one that doesn't have 500 or 25 is D, because it has both the temperature and the volume converted to the correct units that they need to be in. Okay. All right, so number 14. This one, okay, this is similar to some of the ones from earlier. This is an Avogadro's law question, and it's a limiting reactant one. So we have 3 cubic decimeters of ethine, which is this right here, C2H2. And it says it's mixed with 3 cubic decimeters of hydrogen. So that's this reactant. So they've given us both amounts of both reactants. And then if I keep reading, the question asks me, it says, assuming the reaction goes to completion and all gas volumes are measured at the same temperature and pressure, what volume of ethane which is C2H6 is formed? So we're solving for this product. So since they gave us amounts for both reactants, we are going to have to do limiting reactant. But again, because they're all volumes, because I'm starting with volumes of gases and I'm ending with volumes of gases and everything's at the same temperature and pressure, this is where I can use Avogadro's law to kind of do that shortcut that we talked about today in class, where you can simply start with your volume of your gas. So this is the ethine, which is C2H2. And instead of using 22.7 and all that and making it really long, you can simply use the mole ratio. So here and here, there are no coefficients, so that would be 1-to-1 ratio. And that means that it would still stay 3 cubic decimeters for the C2H6, for the ethane. Now, if I do the other one, I'm still starting with 3, but now it's going to be the hydrogen gas, the H2. So my mole ratio is going to be different because the hydrogen has a 2. So it's 2 moles of hydrogen to 1 mole of the product. And so this one, it gets divided by 2. And so 3 divided by 2 is 1.5. And then if you remember that for limiting reactant problems, the smaller number is always the correct answer for the product. So that means that our answer would have to be A on that one. All right, so next one. What volume in cubic meters, okay, so I'm solving for volume, it's cubic meters, is occupied by 2 moles, okay, of a gas, and it's at 27 degrees Celsius, and it's let me switch colors again, and it's at 2 atmospheres of pressure. So this is similar to the one that we just looked at up here, number 13. It's really similar. It's just we're solving for the volume instead of the pressure. But it's the same concept. You're going to use that ideal gas equation. You're going to rearrange it and plug your numbers in and look for the correct answer choice. The only thing, again, and this is what always trips people up, is you got to pay attention to your units. So this 27 has to be converted to Kelvin. So 27 plus 273 is 300 Kelvin. And so 27 shouldn't be in the equation. So here in A, I see 27, so I know A is not going to be right. B has a 27, so I know B is not going to be right. So I can eliminate both of those just based on the temperature. And then that gets me down to C and D. And so if I think about my equation, PV equals nRT, and we're solving for volume on this one, so it's going to be nRT over the pressure. And so I know, but they both have 2 for the number of moles. They both have 8.31 for the R. They both have 300 for the correct temperature. What's different is what's here on the bottom, okay? What's here on the bottom, in C it has 2 times 1.01 times 10 to the 5th. And on the bottom it just has 1.01 times 10 to the 5th. So the correct answer is going to be C. And the reason is because if you remember in this ideal gas equation, our pressure always has to be in pascals, which is PAs. And in the problem up here, they gave me atmospheres. So I would have to convert that number to atmospheres. And I'm sorry, to pascals. And so I would do that. The way I would convert it is I would do 2 atmospheres. And then right here in the problem, they tell me 1 atmosphere is this many pascals. So if I set that up to convert, 1 atmosphere is 101 times 10 to the 5th pascals. So you see that they're being multiplied, and so that is what's in the denominator for the pressure, okay? And so that's why it's C. It can't be D because we have to factor in the fact that it says 2 atmospheres in the problem, okay? So again, a lot of these questions, guys, are really testing whether or not you're paying attention to like units and converting, okay? All right, we got 2 more, so let's look at this next one. I'm going to erase this a little bit. Okay, so this next one, it says, let's see, we have 1 cubic decimeter of an ideal gas, and it's at 100 kPa, and the temperature is 25 degrees Celsius, and then it's heated to 50 degrees Celsius. Notice that it says it's at constant pressure. So guess what? Constant pressure, that means that this 100 kilopascals doesn't matter because it's constant pressure. So they want to know what is the new volume. So this one, we have a V1, we have a V2, that's what we're solving for. And then we have a T1 and a T2. So again, you can set up the math. This is another Charles law equation because it's got volume and temperature. You can set up the math and do it, or you can convert both of these to Kelvin, okay, and then kind of compare them and see if you can figure it out without actually doing the math, just using the fact that they're directly related, okay? What I don't want you to do is fall into the trap. A lot of you guys, what you'll do is you'll say, oh, 25 to 50, that doubled. So that means this must double, and the answer is D. Okay, that's not going to be correct. And the reason for that is this temperature has to be in Kelvin before we can compare them. So what I need to do is I need to add 273 to both of these. Okay, so I get 298 Kelvin, and then for the other one, I get, what was that, 323 Kelvin. So if I compare those, that's definitely not doubling. 298 and 323, definitely not doubling. So it cannot be D. And that's what most of you guys will pick just because you'll forget to, the temperature needs to be converted to Kelvin before you can compare. Okay. Now, here's where you get away with not doing the math and using the big equation. Because even though it's not doubled, it did still increase, right? It went up from 298 to 323. And if we know from Charles' law that if the temperature goes up, the volume will also go up by the same factor, right? Well, the temperature went up, but it didn't double, so it's not D, but it did go up. So that means our new volume has got to be higher than 1. It's got to be a number bigger than 1. And if I look at my other 3 answer choices, only one of them is bigger than 1, letter C. Okay, the other 2 are smaller than 1, which would not follow this relationship. Okay, so again, you can plug them into the equation and do that, but on this problem, remember, you don't have a calculator. So you really need to understand that relationship between temperature and volume and the fact that it is direct. And since our temperature did increase, it didn't double, but it did increase, that means the answer for V2 has to be larger than 1, has to be bigger than this original volume we started with. And so the only answer choice that possibly fits that would be C. All right, last one here. Let me switch colors back. All right, on this one it says the volume of an ideal gas at 27 degrees. Okay, so we have a temperature there. The volume is increased from 3 to 6. Okay, and then it says at what temperature in degrees Celsius will the gas have the original pressure? Okay, so what you have to think about here, guys, is the fact that your volume's doubling, okay? You need to convert temperature to Kelvin, because before you do any calculations, so let's go ahead and do that. So 27 plus 273, so that's 300 Kelvin. So we have 300 Kelvin here, and then we have V1 and V2, and it's doubling because it went from 3 to 6. And so in order for the original pressure to stay the same, that means that the temperature would have to change enough that the volume wouldn't affect it. And so if I think about this, okay, excuse me,